Welcome to our comprehensive guide on building containers. This is a crucial skill for modern application deployment, especially when working with cloud platforms like Google Cloud Run. Think of containers like shipping containers in the real world. Just as shipping containers standardize how goods are transported across different ships, trucks, and trains, software containers package your application with everything it needs to run consistently across different environments. Containers provide several key benefits that make them essential for modern application deployment. They ensure consistent deployment across different environments, provide isolated and secure runtime environments, enable easy scaling and resource management, and accelerate development cycles. Google Cloud Run is a serverless container platform that perfectly demonstrates why container skills are so valuable. It automatically scales your containerized applications from zero. You only pay for what you use, and you can deploy any containerized application without managing servers. Throughout this chapter, we'll explore Artifact Registry for storing your container images, container isolation and security principles, multi-stage builds and optimization techniques, advanced tools like Gib, and Cloud Build, and complete deployment workflows that tie everything together. Remember, containers are the foundation of modern cloud-native application deployment. By mastering these skills, you'll be able to deploy applications efficiently on platforms like Google Cloud Run and many others. Let's begin this exciting journey into the world of containerization. Artifact Registry is Google Cloud's centralized service for hosting and distributing container images and other build artifacts. Think of it as your personal warehouse for all your containerized applications. Picture Artifact Registry as a central hub or warehouse. This is where all your container images live, organized and ready to be deployed whenever you need them. Your Artifact Registry can store multiple container images. Each image represents a different version of your application, like a web app, API service, database, or background worker. All these container images are stored and organized within your Artifact Registry. This creates a single source of truth for all your containerized applications. Now here's the crucial part. When you want to deploy to Cloud Run, you must push your container image to Artifact Registry first. Cloud Run cannot access images from anywhere else. First, your build process must push the container image to Artifact Registry. This is a mandatory step. There's no way around it. Then, and only then, can Cloud Run pull the image from Artifact Registry for deployment. Cloud Run exclusively pulls images from Artifact Registry. It cannot access images from Docker Hub, your local machine, or any other registry. This workflow is not optional, it's required. Artifact Registry serves as the mandatory bridge between your development environment and Cloud Run deployment. Let's summarize the key takeaway. Artifact Registry is your central container image repository. Every Cloud Run deployment must go through this hub, no exceptions. Container isolation is one of the most important security features in containerization. Think of it as giving each container its own secure sandbox where it can play safely without affecting other containers or the host system. This isolation is provided by the Linux kernel, which acts as a smart orchestrator. The kernel uses several mechanisms to trick each container process into thinking it has its own completely isolated system resources. The first type of isolation is file system isolation. Each container gets its own private file system view. Even though containers might share the same host machine, each container sees only its own files and directories, completely unaware of what other containers have. The second isolation mechanism is process namespace isolation. Each container can only see its own processes running. From inside a container, it looks like the container's main process has process ID 1, and no other system processes are visible. This creates a completely isolated process environment. The third isolation mechanism is the virtual network stack. Each container gets its own network interface, IP address, and routing table. Containers can communicate with each other and the outside world through controlled network bridges, but they cannot directly access each other's network traffic. These three isolation mechanisms work together to create a secure sandbox environment. The Linux kernel ensures that containers cannot interfere with each other or access resources they shouldn't have access to. This isolation is what makes containers both secure and efficient for running multiple applications on the same host system. The from instruction is the most fundamental command in any Docker file. Think of it as laying the foundation for a house. Everything else you build depends on this solid base. Every Docker file must start with a from instruction. This command specifies the base image that will serve as the starting point for your new container image. Let me show you how this works visually. Imagine building a container like constructing a building. The from instruction provides the foundation layer that everything else sits on top of. The base image contains the operating system, essential libraries, and tools. When you specify from Ubuntu latest, you're getting a complete Ubuntu operating system as your starting point. There are many different base images you can choose from, each designed for specific purposes. Let me show you some popular options. Ubuntu is great for general-purpose applications and when you need a full Linux environment. Alpine Linux is much smaller and perfect for production deployments where size matters. For specific programming languages, you can use specialized base images. Node.js applications can start with the official Node image, while Python applications can use the Python base image. The from instruction essentially overwrites everything with the contents of the base image. This means your container starts with a clean slate containing only what the base image provides. Here are the key takeaways about the from instruction. It must be the first instruction in your Docker file. It determines your starting environment. And choosing the right base image affects your final container size and security. Container image size might seem like a minor detail, but it has major implications for production deployments. Today, we'll explore why keeping your container images small is crucial for both performance and security. The first major benefit of small container images is faster deployments. When you deploy a container, the entire image must be downloaded to the target environment. Less data means faster transfers. This speed difference becomes critical in production environments where you might need to scale quickly during traffic spikes or when doing frequent deployments as part of continuous integration and delivery pipelines. The second major benefit is security through reduced attack surface. Every library, tool, and system component in your container image represents a potential vulnerability that attackers could exploit. By removing unnecessary components like development tools, documentation, and unused libraries, you eliminate potential entry points for attackers. This principle is called minimizing the attack surface. Here are some practical strategies to keep your container images small. Use minimal base images like Alpine Linux or distro-less images. Combine multiple run commands to reduce layers, and remove package caches and temporary files after installation. Remember, small container images lead to faster deployments and improved security. Every megabyte you remove makes your application more efficient and secure in production environments. Multi-stage Docker files are a powerful technique that allows you to create lean, efficient container images. Instead of having one large, bloated image with all your build tools, you can separate the building process from the final runtime image. The traditional approach creates one large image that contains both build tools and your application. This results in unnecessarily large images that include compilers, development libraries, and other tools that aren't needed at runtime. Multi-stage builds solve this problem by using multiple from instructions in a single Docker file. Each from instruction starts a new build stage, and you can copy only what you need from previous stages using the copy from instruction. The key instruction is copy from, which allows you to copy files from a previous build stage. You can reference stages by number, starting from 0, or give them names for better readability. Here's a complete example of a multi-stage Docker file for a Node.js application. The first stage builds the application, and the second stage creates a lean production image with only the built artifacts. The benefits of multi-stage builds are significant. You get dramatically smaller images, improved security by removing build tools from production, faster deployment times, and better separation of concerns between build and runtime environments. Distroless images represent the ultimate in container minimalism. They contain just enough dependencies to run your application and absolutely nothing more. Let's compare a regular container image with a distroless image to understand the difference. Notice how much smaller the distroless image is. A regular container image contains many components. It has a shell for debugging, a package manager for installing software, extensive system libraries, plus your application and its runtime dependencies. In contrast, a distroless image contains only your application and the absolute minimum runtime dependencies needed to execute it. Everything else has been stripped away. Notice what's missing from the distroless image: no shell, no package manager, and no unnecessary system libraries. This creates a much smaller and more secure container. Distroless images provide three major benefits that make them ideal for production environments. First, they're ultra small in size. Without unnecessary components, distroless images are dramatically smaller, leading to faster deployments and reduced storage costs. Second, they provide enhanced security. With no shell or package manager available, attackers have a much smaller attack surface to exploit if they gain access to your container. Finally, they're production optimized. Distroless images contain only what's absolutely necessary to run your application, making them perfect for production deployments where reliability and efficiency matter most. Here's a practical example of the size difference. A typical Ubuntu-based container image might be around 200 megabytes, while the equivalent distroless image could be as small as 20 megabytes. That's a 90% reduction in size. Distroless images represent the philosophy of including only the bare essentials. They're perfect for production environments where security, size, and performance are critical considerations. When developing containerized applications, you need a way to test them locally before deployment. Port mapping is the bridge that connects your local development environment to your running container. Port mapping allows you to access services running inside a container from your local machine. Think of it as creating a tunnel between your computer and the container. The Docker run command with the -p flag creates this port mapping. Let's break down the command. Docker run -p9000 8080. The format is local port :container port. Port 9000 is on your local machine, and port 8080 is inside the container where your application is running. Now let's see how this works in practice. When you make a request to localhost 9000 in your browser, Docker forwards that request to port 8080 inside the container. Here's the complete request flow. Your browser sends a request to localhost 9000. Docker receives it and forwards it to the application running on port 880 inside the container. This port mapping is essential for local development and testing. You can test your containerized application as if it were running directly on your machine, but with all the benefits of container isolation. Remember, the first number is always your local port, and the second number is the container port. This mapping creates a seamless bridge between your development environment and your containerized application. Traditional containerization requires writing Docker files manually, but tools like Co for Go and Gib for Java offer a much simpler approach by automating the entire process. The traditional approach requires writing a multi-stage Docker file, configuring build stages, handling dependencies, and manually building and pushing images. This involves many manual steps and potential for errors. In contrast, Co for Go applications and Gib for Java applications provide a single command solution. Co build and Maven Gib build handle everything automatically, no Docker file required. Here's how these tools streamline the process. They take your source code, perform static compilation to create a single binary, package it in a minimal distroless image, and automatically push it to your container registry. The key benefits are clear: faster development without Docker file maintenance, better security with distroless images by default, and smaller optimized images. These simple commands replace complex multi-stage builds. These tools represent the evolution of containerization, from manual configuration to automated, opinionated workflows that follow best practices by default, making containerization accessible to all developers. Cloud-native build packs provide a revolutionary, standardized approach to transforming your source code directly into container images, eliminating much of the complexity traditionally associated with containerization. The key advantage of build packs is their universal nature. Anyone can create a build pack for any programming language or runtime environment, making this approach incredibly flexible and extensible. The pack command line tool is the orchestrator that makes this magic happen. It intelligently analyzes your source code and automatically detects the most appropriate build pack to use. Here's a concrete example. When the pack tool encounters a package.json file in your project directory, it immediately recognizes this as a Node.js application and automatically selects the appropriate Node.js build pack. This standardized approach eliminates the need to write complex Docker files for many common use cases. The build pack handles all the intricate details of creating an optimized container image for your specific runtime environment. Cloud-native build packs represent a significant step forward in containerization, providing developers with a simple, standardized way to package applications without deep container expertise, while maintaining the flexibility to customize when needed. Google Cloud Build is much more versatile than just building container images. It's a powerful automation platform that can execute a wide variety of tasks in sequence. Cloud Build operates on a shared workspace directory. All build steps can access and modify files in this common space, allowing data to flow between different operations. Cloud Build executes programs consecutively, one after another. Each step can use the results from previous steps, creating a powerful automation pipeline. Cloud Build can handle many different tasks. It can run unit tests to verify your code, perform static analysis to catch issues, deploy containers to services like gcp-cloudrun, and execute long-running administrative tasks like database migrations. One of Cloud Build's key advantages is its generous 24-hour timeout. This means you can run long-running tasks, complex multi-step workflows, and administrative operations without worrying about time constraints. To summarize, Cloud Build is a versatile automation platform that goes far beyond just building images. It can execute sequential programs, share data through a common workspace, run for up to 24 hours, and handle everything from testing to deployment. In building container images, developers face an important choice between using traditional Docker files and modern higher-level tools. Each approach has distinct advantages and trade-offs that affect your development workflow. On one side, we have traditional Docker files, the standard way to define container images with explicit instructions. On the other side, we have higher-level tools like Co and Gib that abstract away much of the complexity. Docker files provide fine-grained control and full customization options. They're the industry standard and offer complete transparency in the build process. However, they require complex syntax knowledge, manual optimization, and careful security considerations. Higher-level tools like Co and Gib offer simplified workflows with automatic optimization and built-in best practices, leading to faster development. But they provide less control, require tool-specific knowledge, and have limited customization options. Now let's examine the key trade-offs you need to consider when choosing between these approaches. The primary trade-off is between control and simplicity. Docker files give you maximum control, but require more complexity, while higher-level tools prioritize simplicity at the cost of some control. Choose Docker files when you need complex multi-stage builds, custom base images, or fine-tuned optimization. Choose higher-level tools for rapid development cycles, standard application patterns, or when your team prefers simplicity over control. Remember, there's no universally correct choice. The best approach depends on your specific requirements, team expertise, and project constraints. Many organizations use both approaches for different types of applications. Container isolation is one of the most critical aspects of modern containerization technology. Today, we'll explore why proper isolation is essential for security and what happens when it fails. Container isolation creates secure boundaries between running applications. Think of it like having separate apartments in a building. Each container gets its own private space that other containers cannot access. The Linux kernel achieves container isolation through two key mechanisms: namespaces and cgroups. Namespaces provide process isolation, while cgroups control resource allocation and limits. Linux provides several types of namespaces, each isolating different aspects of the system. PID namespaces isolate process IDs, Network namespaces separate network interfaces, and mount namespaces control file system access. When container isolation fails, serious security vulnerabilities emerge. Containers might access the host file system, escape to other containers, or consume unlimited system resources, potentially compromising the entire system. To maintain strong container isolation, follow these key practices. Run containers as non-root users, implement proper resource limits, keep container images minimal, and regularly update your container runtime and kernel. Container isolation is not just a technical feature. It's a fundamental security requirement. Understanding how namespaces and C groups work helps you build more secure containerized applications and avoid common pitfalls that could compromise your entire infrastructure. When building containers for Cloud Run, you have two main approaches: building locally with Docker on your machine or using Google Cloud Build in the cloud. Each has its place in your development workflow. Local Docker development gives you immediate feedback and fast iteration cycles. When you make changes to your code, you can quickly rebuild and test your container right on your development machine. However, local Docker has some limitations. Your builds depend on your specific machine setup, which can lead to the classic "it works on my machine" problem. Different developers might get different results. Cloud Build, on the other hand, runs your builds on Google Cloud infrastructure. This ensures consistency across your team and provides virtually unlimited scalability for complex builds. Cloud Build does have some trade-offs. There's a slight delay since builds happen remotely, and you need an internet connection. It's also more complex to set up initially compared to local Docker. The best practice is to use both approaches strategically. Use local Docker during development for quick testing and iteration. Then use Cloud Build for your production deployments to ensure consistency and reliability. Here's a practical example. During development, you might run Docker Build and Docker Run locally dozens of times as you refine your application. Once you're ready to deploy, you push your code and let Cloud Build create the production image. Key takeaways: local Docker is perfect for development with its speed and immediate feedback. Cloud Build ensures production consistency and scalability. Use local Docker to develop and iterate quickly, then rely on Cloud Build for your production deployments to Cloud Run. Distroless images represent a revolutionary approach to container security and efficiency. These specialized container images contain only your application and its runtime dependencies, stripping away everything else, including shells, package managers, and debugging tools. To understand the impact of distroless images, imagine two containers side by side. A traditional container image includes the full operating system, shell, package managers, and debugging tools alongside your application. In contrast, a distroless container contains only your application and the minimal runtime dependencies needed to execute it. Everything else has been removed, creating a much leaner and more secure container. The security benefits of distroless images are substantial. By removing shells, package managers, and debugging tools, you dramatically reduce the attack surface. Attackers have fewer entry points and tools available if they manage to compromise your container. Distroless images also provide significant efficiency benefits. Smaller image sizes mean faster deployment times, reduced storage costs, and quicker container startup. Your applications can scale more rapidly when each container requires less time and resources to initialize. However, distroless images come with debugging challenges. Without a shell or debugging tools, troubleshooting issues becomes more complex. You cannot simply exec into the container to investigate problems or run diagnostic commands. The decision to use distroless images requires weighing these trade-offs carefully. For production environments where security and performance are paramount, the benefits often outweigh the debugging challenges. However, teams must invest in proper logging, monitoring, and alternative debugging strategies to maintain operational effectiveness. The Cloud Run deployment workflow is a streamlined process that takes your source code and transforms it into a running, scalable application. Understanding each step helps you build and deploy applications efficiently. The workflow begins with your source code. This includes your application files, a Docker file that defines how to build your container, and all the dependencies your application needs to run. Next comes the build process, where your source code is transformed into a container image. You have several options here: traditional Docker builds, Go for Go applications, Gib for Java, or cloud-native build packs for automatic detection. The built container image is then stored in Artifact Registry, Google Cloud's secure container registry. This acts as your image hub, providing version control, security scanning, and reliable storage for your container images. Finally, Cloud Run pulls your container image from Artifact Registry and deploys it as a serverless application. Cloud Run provides automatic scaling, pay-per-use pricing, and handles all the infrastructure management for you. Each component in this workflow plays a vital role. The source code provides the foundation, the build process creates the deployable artifact, Artifact Registry ensures secure storage and distribution, and Cloud Run provides the scalable runtime environment. Artifact Registry is Google Cloud's modern service for hosting and distributing container images and other build artifacts. It serves as the successor to the older Container Registry service. Here's how Artifact Registry fits into your development workflow. Developers push their container images to Artifact Registry, which then serves as the central repository for deploying to services like Cloud Run. Artifact Registry provides several key advantages over the older Container Registry. It offers enhanced security with fine-grained access control, supports multiple artifact formats beyond just Docker images, includes advanced versioning and tagging capabilities, and provides regional replication for better performance worldwide. The key takeaway is that Artifact Registry serves as your central hub for storing and distributing container images in Google Cloud. It's an essential component in modern cloud-native development workflows, providing the reliability and security needed for production deployments. Cloud Build is a Google Cloud service that allows you to build container images remotely on Google Cloud infrastructure. But it's much more than just an image builder. It's a complete build automation platform. Cloud Build offers several key capabilities that make it powerful for modern development workflows. It can build container images from your source code, execute custom build workflows, automatically trigger builds from code changes, and integrate seamlessly with other Google Cloud services. Here's how a typical Cloud Build workflow operates. It starts with your source code in a repository, processes it through Cloud Build, which can run multiple build steps and produces a container image that's ready for deployment. The key takeaways about Cloud Build are that it's a comprehensive build automation service, not just a container image builder. It can execute complete workflows remotely, integrates seamlessly with the Google Cloud ecosystem, and supports modern CI/CD practices with automated triggers and deployments. Cloud Run is a key term in modern cloud computing. Let's break down what this powerful service actually means and how it works. Let's break this definition into two key parts. First, what does serverless platform mean? Serverless doesn't mean there are no servers. It means you don't have to manage them. The second part is containerized applications. This means your code is packaged into containers, lightweight, portable units that include everything needed to run your application. Here's how Cloud Run works in practice. You provide a container image, and Cloud Run handles everything else, from scaling to load balancing to security. The key benefits of Cloud Run make it perfect for modern applications. You get automatic scaling from 0 to thousands of instances. You only pay when your code is actually running, and you can deploy in seconds. In summary, Cloud Run is Google Cloud's serverless container platform that eliminates infrastructure management while providing automatic scaling and cost efficiency. It's the bridge between traditional containers and serverless computing. A container image is one of the most fundamental concepts in modern software deployment. Think of it as a complete, self-contained package that has everything your application needs to run. Let me show you what goes inside a container image. It's like a shipping container that holds everything needed for your application to work properly. Inside this container image, we have your actual program or application code. This is the software you've written that does the work. But your program can't run by itself. It needs libraries. These are pre-written code modules that provide additional functionality your application depends on. The container image also includes static assets like images, style sheets, or data files that your application needs to function properly. Finally, it contains configuration files that tell your application how to behave in different environments and situations. Here's a concrete example. Imagine you've built a web application using Python. Your container image would include your Python code, the Python runtime, web framework libraries like Flask, any HTML and CSS files, and configuration files for your database connections. The key benefit is portability and consistency. Once you create a container image, it will run the same way on your laptop, on a test server, or in production. Everything needed is bundled together. Remember, a container image is like a snapshot of your application and everything it needs. It's the foundation that makes modern cloud deployment possible, ensuring your software works reliably across different environments. Container isolation is a fundamental concept in containerization technology. It refers to the process by which the Linux kernel separates a running container and its processes from other processes and the host system. Imagine a host system running the Linux kernel. Within this system, we can have multiple containers running simultaneously. Each container appears to be isolated from the others and from the host system itself. The Linux kernel creates invisible barriers around each container. These barriers ensure that processes inside one container cannot interfere with processes in other containers or access the host system directly. Container isolation provides three key components that create this separation. First, each container gets a private file system, meaning it has its own view of files and directories that other containers cannot access. Second, containers have their own network stack with isolated network interfaces and IP addresses. This means network traffic in one container doesn't interfere with another container's networking. Third, each container operates in its own process namespace. This means processes running inside a container have their own process ID space, separate from the host system and other containers. Container isolation provides several critical benefits. First, it enhances security by preventing containers from accessing each other's data or interfering with the host system. It also enables precise resource control, allowing system administrators to allocate specific CPU and memory limits to each container. Container isolation ensures predictability, meaning applications run consistently across different environments, and provides portability so containers work the same way on any Linux system. The key takeaway is that container isolation is the Linux kernel's fundamental mechanism for creating secure, separate environments. This isolation ensures that containers cannot interfere with each other or the host system, making containerization both safe and reliable. The copy instruction is one of the most fundamental commands in Docker. It's used to copy files and directories from your local build context into the container image. Think of copy as moving files from your local computer into the container. On the left, we have your build context, the local files and directories. On the right, we have the container image, where these files will be copied. The copy instruction creates a bridge between your local files and the container. Each file or directory you specify gets copied into the container image at the location you define. The copy instruction follows a simple syntax pattern. You specify the source file or directory from your build context, followed by the destination path inside the container. Here are three common examples. First, copying a single file like your main application file. Second, copying an entire directory like static assets. Third, copying multiple files at once to the same destination. Here are the key takeaways about the copy instruction. It transfers files from your build context to the container, preserving permissions and metadata. The source path is relative to your build context, while the destination is an absolute path inside the container. Copy is essential for including your application code and assets in the container image. Understanding copy is crucial for building effective Docker images. It's the bridge that brings your local application files into the containerized environment where they can run. Distroless refers to a project that creates minimal container images. These images contain only the essential dependencies required to run an application. Let's compare a regular container with a distroless container. A regular container includes many components like a shell, package manager, and various system tools. In contrast, a distroless container strips away everything unnecessary. It contains only the runtime dependencies and your application. No shell, no package manager, no extra tools. Notice what's missing from the distroless container. No shell means no command line access. No package manager means you can't install additional software at runtime. This minimal approach provides significant benefits. Let's explore why distroless containers matter. Distroless containers offer 3 key advantages. First, enhanced security through a smaller attack surface with fewer potential vulnerabilities. Second, better performance with faster startup times and smaller image sizes, which means quicker deployments and lower storage costs. Third, easier compliance, since there are fewer components to audit, patch, and maintain over time. Here are the key takeaways about distroless containers. Distroless containers contain only essential runtime dependencies. They exclude shells, package managers, and system tools. This provides better security and performance, making them ideal for production deployments where you want minimal, secure containers.